Hello friends, in the previous videos we showed you how to solve a 2D transient heat conduction problem in Cartesian coordinates using FTCS and BTCS finite difference methods. In this video we're going to solve a 2D transient heat conduction problem in Cartesian coordinates using ADI or alternating direct implicit finite difference method. Our objectives are to present a simple 2D transient heat conduction problem with no heat generation. We will then discretize the domain into a 4x4 grid. We will consider two half-time steps and solve the problem using ADI finite difference method. We will then vary the grid spacings and time steps and resolve the problem and obtain temperatures inside the domain. Our domain is a square copper plate. The initial temperature of the copper plate is 200 degrees Celsius. The material property called thermal diffusivity, represented by alpha, equals 1 e to the negative 4 meter square per second. At time t greater than or equal to 0, the temperatures at all four sides of the copper plate are maintained at 100 degrees Celsius. Our objective is to find the temperature profile inside the copper plate at various locations with time. The x and y coordinates are shown on the left-hand side of the sketch. The general heat conduction equation in 3D Cartesian coordinates is given as dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus g over k equals 1 over alpha times dou t over dou t, where the uppercase t represents the temperature in the domain and is a function of x, y, and z, the three spatial coordinates, and time represented by lowercase t in seconds. Alpha equals the thermal diffusivity, which is a material property and is given in meter square per second. Alpha equals K over rho C, where K is the thermal conductivity of the material in watts per meter Kelvin. Rho is the density of the material in kilograms per meter cube. C is the specific heat capacity of the material in joules per kilogram Kelvin, and G is the volumetric rate of internal heat generation in watts per meter cube. We assume that the thermal conductivity in the domain is homogeneous in isotropic. Accordingly, the thermal conductivity K is uniform in the domain. For 2D transient heat conduction with no heat generation, equation 1 reduces to a simpler form. We assume that the temperature does not vary significantly along the z direction when compared with x and y directions. Also, there is no heat generation term involved, so G equals 0. Dou square t over dou x square plus dou square t by dou x square equals 1 over alpha times dou t over dou t, and t is a function of x, y, and t. Equation 2 can be rearranged as dou t over dou t equals alpha times dou square t by dou x square plus dou square t by dou y square. T is a function of x, y, and t, and time greater than or equal to 0. The initial condition is given as t at x, y, t equals 0 equals t in. The boundary conditions are t at x, y equals 0, t equals t1, t at x equals L, y, t equals t2, t at x, y equals w, t equals t3, t at x equals 0, y, t equals t4. These are the boundary conditions at the four sides of the copper plate. L represents the length of the domain in x direction and W represents the length of the domain in y direction. To obtain the temperature profile, we need to solve the above PDE. We will utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. We will follow the procedures as shown in the next slide for the ADI method. For the first ADI step, we have Ti, Jn plus half minus Ti, Jn over delta t by 2 equals alpha times ti minus 1 comma jn minus 2 times ti comma jn plus ti plus 1 comma jn by delta x square plus ti comma j minus 1 n plus half minus 2 times ti comma j n plus half plus ti comma j plus 1 n plus half by delta y square. Here the temperature variation in the first time step is along the y direction as shown in equation 4. For simplicity, let delta x equals delta y. Also let d equals alpha times delta t by delta x squared, where d is the diffusion number. We then get ti comma j n plus half minus ti comma j n equals d over 2 times ti minus 1 comma j n plus ti plus 1 comma j n minus 2 times ti comma j n plus ti comma j minus 1 n plus half minus 2 times ti comma j n plus half plus ti comma j plus 1 n plus half. We'll rearrange this equation as shown in equation 5, which is minus d times ti comma j minus 1 n plus half plus 2 times 1 plus d times ti comma j n plus half minus d times ti comma j plus 1 n plus half equals d times ti minus 1 comma j n plus 2 times 1 minus d times ti comma j n plus d times ti plus 1 comma j n. Here the left hand side of the equations are the unknowns and the right hand side of the equation is known. In general, equation 5 is the finite difference approximation for the first ADI step of the original equation we were trying to solve. Here I represents the node location along the x direction, and j represents the node location along the y direction, and n represents the time step. For the second time step, we have ti comma j n plus 1 minus ti comma j n plus half by delta t by 2 equals alpha times ti minus 1 comma j n plus 1 minus 2 times ti comma j n plus 1 plus ti plus 1 comma j n plus 1 by delta x square plus ti comma j minus 1 n plus half minus 2 times ti comma j n plus half plus ti comma j plus 1 n plus half by delta y square. Here the temperature variation is considered along the x direction with time as shown in equation 6. Again, for simplicity, let delta x equals delta y and d equals alpha times delta t by delta x squared. Then the equation gets simplified and we'll rearrange the equation as shown in equation 7, that is minus d times ti minus 1 comma j n plus 1 plus 2 times 1 plus d times ti comma j n plus 1 minus d times ti plus 1 comma j n plus 1 equals d times ti comma j minus 1 n plus half plus 2 times 1 minus d times ti comma j n plus half plus d times ti comma j plus 1 n plus half. Here the left hand side of the equation is unknown and on the right hand side of the equation the temperatures are known in general. Equation 7 is the finite difference equation for the second ADI step of the original equation we were trying to solve. Here I represents the node location along the x direction and j represents the node location along the y direction and n represents the time step. The above approximation is called alternating direct implicit or ADI method. This is an implicit method, hence temperatures Tij's at future times n plus 1 etc. need to be obtained based on Tij's at present times as shown in equation 5 and 7. Equations need to be solved simultaneously as we have unknown temperatures at neighboring points for the same time step. The advantage being implicit methods are unconditionally stable, but the diffusion number t and time step delta t still need to be smaller for accuracy considerations, not stability considerations in general. The truncation error is of the order of delta t square plus of the order of delta x square plus of the order of delta y square. So the truncation error on the time variable is of the order of delta t square as shown. When compared with FTCS and BTCS methods, the truncation error for time was of the order of delta t. So this is an improvement with using an ADA method. Now let us discretize the 2D domain into a 4x4 grid equally spaced as shown below. Here Tin is the initial temperature in the entire domain, and T1, T2, T3 and T4 are the temperatures at the sides of the copper plate and the boundary conditions maintained at time greater than or equal to 0. We have 25 nodes in total. Temperatures are fixed at the boundary nodes as shown. Our interest is on the 9 interior nodes from 2,2 to 4,4. Let us apply equation 5 on the 9 interior node, that is the first ADI time step, or the first half time step, the ADA method. Accordingly, we get a set of equations as shown. So we can move the boundary nodal temperatures which are present on the left hand side to the right hand side. By rearranging, we get the set of equations as shown here. For simplification purposes, let beta equals 2 times 1 plus d and gamma equals 2 times 1 minus d. We then get the set of equations arranged as shown. We'll rearrange this set of equations in a matrix form. As shown here. Here the temperatures at the n plus half time step are the unknowns, and the temperatures at the nth time step is the previous time step, and they are known. The right hand side vector t, for example t1, 2 plus t2, 1 and t1, 3 etc. they represent the boundary conditions. The equation is of the form a times t n plus half equals b times t n plus c. Here the A matrix shown is a tridiagonal matrix. The above set of equations can be solved using Thomas algorithm method. We can also use iterative methods such as Gauss-Seidel or successive over-relaxation method. Let delta t equals 100 seconds. Note here that we are using a higher value for delta t for illustration purposes. For accuracy purposes, we need to use a smaller value. Here delta x equals L over nx equals 1 over 4 equals 0.25 meters. Delta y equals delta x equals 0.25 meters. The diffusion number d equals alpha times delta t by delta x squared, which is equals to 0.16, which is lesser than the stability criteria for the FTCS method or the explicit method. Here we don't need to comply with the stability criteria, but it is given only as a reference. Beta equals 2 times 1 plus d, which is equal to 2.32, and gamma equals 2 times 1 minus d, which is equal to 1.68. We will now substitute the values of the diffusion number d, beta, gamma, the initial and previous time steps, and boundary conditions. also we'll substitute n equals 0. Accordingly, our set of equations are arranged this way. We can solve the above equation using Thomas algorithm method on MATLAB as mentioned earlier, and we get the following results. For the first half time step, there is delta t by 2 equals 50 seconds. These are the internal nodal temperatures at the various nodes. For the second time step, we follow a similar procedure using equation 7. And the set of equations is shown here. Again, we'll move the known boundary nodal temperatures from left hand side to the right hand side of the equations, and we'll let beta equals 2 times 1 plus t and gamma equals 2 times 1 minus t. We then get the set of equations arranged in the form shown here. We will rearrange the set of equations in the matrix form as shown here. Again, here the temperatures at the n plus 1 condition time step are the unknowns, and the temperatures at n plus half time step, which is the previous half time step, they are known. And the right hand side vector represents the boundary conditions. This equation is of the form a times t n plus 1 equals b times t n plus half plus c. So again, for the second time step, the A matrix shown is similar to the first time step of the ADI. A matrix is a tridiagonal matrix. We can solve the above set of equations using TA method or iterative methods. We'll substitute the values of beta, t, gamma, etc. Accordingly, we get the set of equations arranged in the matrix form. Using Thomas algorithm method, we can solve the above set of equations and we can obtain the nodal temperatures which are shown here. We'll now go back to MATLAB. Here, alpha represents the material property called thermal diffusivity, as discussed earlier. We have a total time of say 200 seconds. A number of time steps equals 2. So delta t equals t over nt, which is 100 seconds. And the length of the plate shown as x length is 1. And the y length is the same as x length. And number of spatial grids is shown nx as 4. And delta x equals x length over nx, which is equal to 1 over 4 equals 0.25. The four boundary temperatures are maintained at 100 degrees Celsius and the initial temperature is 200 degrees Celsius. We will run this program now. Here the diffusion number D is given as 0.16. A is the tridiagonal matrix which we have seen. This matrix is the same for the first time step as well as the second time step, the second half time step of the ADA method. UA, DA, and IA are the upper diagonal matrix vector, the diagonal vector, and the lower diagonal vector. These are derived from the A matrix, so we can easily apply this using Thomas algorithm method. And B is the matrix on the right hand side. For the first time step of 50 seconds, we have the temperatures given here. And this may be a little bit different than what's shown on the PowerPoint, as in this particular case I interchanged I and J coordinates. And for the second time step, second half time step, these are the final nodal temperatures. Likewise, the third half time step and the fourth half time step, which represents 150 seconds for the third half and 200 seconds for the fourth half, is shown here. We'll go to the graphics window now. Here on the left hand side top portion, the initial temperature of the copper plate is shown. The temperatures we see is about 200 degrees Celsius. On the left hand side bottom portion, we have the final temperature profile. The boundary conditions are 100 degrees Celsius for all four sides, and the initial temperature is 200 degrees Celsius, and the temperature variation is from about 175 to 195 on the interior nodes. The right hand side gives a animated plot. Now since we only ran it for 200 seconds, it has now stopped. We will now go back to MATLAB and vary our grid spacings. Let t equals 1600 seconds, which is the total time. Number of time steps, let's change it to 160 from 2, and total number of spatial grids, let's change it to 15 from 4, and let's keep the other values the same, and we will rerun this program. So again, the left hand side top portion shows the initial condition, and the left hand side bottom portion shows the final condition when time equals 1600 seconds, and the right hand side shows the animated plot. So on the left hand side bottom portion, for example, the final temperature variation is from, say, about 100 degrees Celsius to about 107 degrees Celsius on the interior nodes, which will be reflected on the right hand side animated plot as well when we reach time equals 1600 seconds. So the plate is cooling. The plate is initially at 200 degrees Celsius. When we maintain the temperatures at all four sides at 100 degrees Celsius, when time t is greater than or equal to 0, the plate starts cooling, and that's what is shown here. The animation will run till we hit 1600 seconds. We can watch this maybe for a little more while. The temperature profile on the animated plot on the right hand side should match the temperature profile shown here at the bottom left hand side at the final condition. So according to the ADI method, the temperature sweep happens along one direction first, and then after a while, after the sweep is done, the sweep goes into the other direction. So this alternates, the sweep alternates, and that is why this is called an ADI, or alternate direct implicit method. Okay, now it has stopped running. We'll go back to our PowerPoint. So we can use the same procedure as I mentioned. We did the first two half-time steps. Likewise, for the next time steps, we can use the same kind of a procedure, and we can solve the above problem. So we presented the graphical results in MATLAB, which we have just seen. To summarize, in this video we presented a 2D transient heat conduction problem. The temperature at each of the four sides of the square copper plate is fixed. The initial temperature in the domain is known. We discretized our domain and solved the problem, and obtained the temperature profile at various interior nodes in the domain using ADI, or alternate direct implicit finite difference method. Note, ADI method is an implicit method and is unconditionally stable. We still need to keep smaller time steps delta t and the diffusion number d for accuracy purposes and not for stability purposes. We varied the grid spacings and time steps and presented the results graphically using MATLAB. In future videos, we can explore more challenging problems. If you have any questions or comments, please post it. Thanks for watching.